Okay, so good afternoon, participants. After introductory section, this introductory session, this is our first lecture on introduction to engine optimization. Okay, so this module again have trapezoidal syllabus like metal forming processes, where some modules were having were assigned more number of lectures, where the module were only of one or two lectures. So similar is the case with the module one of your this course, that is the module one, under which around four lectures have been assigned, but it will hardly require for 30 minutes or more than 40 minutes to cover the syllabus which has been given in the module 1. It is mostly theoretical portion and introduction to optimization, then history, then application areas. So it will take hardly 30 to 40 minutes, and then I will continue as I discussed in the previous class that I will switch to the module 2. So in fact, I will try to skip this historical development uh, in engineering optimization. Okay, so I will share the content which is related to historical development in engineering optimization to you through a PDF uh, through your CR, that is Sati. Okay, so under module one, your first topic is introduction to engine optimization. So by the term, as the name indicate, optimization. So it is well understood that we are optimizing something. Okay. So optimizing means we are obtaining best result under the given certain circumstances. Okay. So this optimization can be defined as the process of finding a condition that gives the maximum or minimum of a function. Okay, so these are the techniques uh, which are also known as mathematical programming techniques and are generally studied as a part of your work. So those some of you might be taking OR as open elective or department elective in uh, coming session, or you might have studies. Okay, so few of these techniques will be taught as a part of your work. Basically, this course was developed as a part of OR. So again, in OR, what we do, uh, we systematically or mathematically study the optimization techniques. That is nothing but it is either maximization or minimization of certain values or certain function, given function, in order to get the best results. Okay, so these best result may be either minimization of certain things, like in the case of if we talk about farming processes, we may like to minimize the material wastage, and we may like to maximize the profit. We may like to maximize the production, but in the same time we may like to minimize the production time. Okay, so this way there may be a case of maximization or minimization in the case of whenever we are optimizing certain parameters based on given certain circumstances or conditions. Okay, so this way we can understand what is optimization. Okay, and in optimization we have certain function. Okay, so suppose here I'm taking one example of certain function fx. uh, okay, and in this this in this function, which is function of x. Okay, so in this function we can see there is certain value. Okay, suppose it is a case of minimization. Suppose we want to, in a metal forming process, it is a function fx, and we want to minimize the production time of any component. Okay, so so in that case we are minimizing, and suppose it is your plot of your corresponding function. Okay, so in that case what we are doing, we are minimizing the production time. Okay, in this case we are minimizing the total function fx. Okay, and the corresponding value, minimum value, that is optimum solution, that is x star. Okay, so here a point x star correspond to the minimum value of function fx, and the same point uh, here. So if we want to, if we are, it is the property of of the mathematical techniques or the optimization techniques, that if we want to get the minimum of a function fx, then we can do the reverse also. We can get the maximum of minus fx, that is the same function with negative sign. Okay, so if you see this is your function fx, then if you multiply by a negative sign, then this function will become minus fx. If you multiply this function by minus 1, then this function will become minus fx. And obviously this will lie on the another side of your x-axis. Okay, so this function minus fx is lying in the negative side. So in the case of fx, the value which we are getting as a minimum of fx will be the process will be remain the same if we are maximizing for minus fx. So in the case of minus fx, this value will be the maximum value. So in certain techniques, if we are able to understand minimization techniques or maximization techniques, because we will be studying both the cases, maximization problem as well as minimization techniques. Okay, so both kind of techniques we will be studying as a part of this course. So if we have studied suppose maximization problem, then we can minimize, we can alter the, we can use the particular technique for the maximization case also by multiplying by a minus sign or by minus 1. Okay, so this way we will be using different techniques because it will not impact on the optimum value of your x. Okay, so there are other functions also which do not affect the optimum value, that is the multiplication or division of your function by a positive constant. Here in the left hand side, you can see there is a function fx, and there is a some optimum value corresponding to your value x. This is your optimum value, and this is your f star is the corresponding optimum value of your function. Suppose if we are multiplying this function by certain constant x, this is not the optimum value of x is not going to change. So here we can see we have multiplied by constant c. So this f star or fx becomes cfx. Okay, and but the value of your optimum point remains the same. That is the x star. Similarly, in the case of addition or subtraction by certain positive constant, say c, this is your second case. In the in right hand side, there is a function fx, and we are adding certain value, certain constant, say c, into your function. Again, it is not going to change or affect your optimum value. So these are certain properties which we will be using, we will be utilizing in your coming optimization techniques while discussing the optimization techniques. Okay, so after this introduction part, some specific uh, properties. In your module 1, there is a small topic, that is the history of optimization. So that I will not cover. It is mostly a theoretical part. So I will share so that you are aware some 2-3 page write up so that you can go through it and you are aware about how these optimization techniques were developed. And we already it is well known in public domain that these the techniques which are known as which are taught as under engineering optimization or which are taught under operations research, all these techniques were developed during the period of World War for for the application of military applications. Okay, so these techniques were developed by mathematicians during the World War One and World War Two, and now these techniques are being used in almost all areas of your mechanical engineering as well as other areas of uh, science courses, that is physics, chemistry, math, or any other engineering stream. Okay, so after this, we will move slightly to the uh, application part of engineering optimization. So, optimization in its broad sense can be applied to solve any engineering problem. Uh, it can be used for design of aircraft, aerospace structure of we may where the desired objective function may be the minimum weight with high strength. Okay, so there may be multiple objectives like minimum weight, requirement of reduced weight or minimum weight with certain given strength of the aircraft component. Next, maybe the finding the optimum trajectories for space vehicles, so that there is less energy wastage or there is less fuel consumption. Uh, you will find vast areas of application if we are talking about engine optimization. These techniques are used everywhere wherever there is some requirement of we expect to get some minimum value or maximum value. Similarly, these techniques may be used to design of civil engineering structures such as frames, foundations, bridges, towers, chimneys, and dams for minimum cost. Okay, next may be the minimum weight design of a structure for earthquake, wind, and other type of random load. So I will quickly read out the major application areas which I have listed out as a part of your today's lecture, and then quickly I will jump to the module 2. Uh, that is from where your numerical portion or the actual discussion on optimization techniques start. Okay, so the next may be the design of water resource system for maximum benefit. Uh, the next one is optimum plastic design of structure. Then we have optical design of linkages, cams, gear, machine tools, and other mechanical components. The next may be selection of machining condition in metal cutting processes for minimum production cost. Okay. Then next may be design of material handling equipment such as conveyors, trucks, cranes for minimum cost. The next is design of pumps, turbine. Uh, just 1 second. So the hello. Yes. So the next may be design of pumps, turbines, and heat transfer equipment for maximum efficiency. Then maybe the optimum design of electrical machineries such as motors, generators, and transformers. Similarly, as I told, the area is not limited to mechanical engineering. These optimization techniques may be used in any stream, electrical, electronic, civil, mechanical, or any area wherever you can think of. shortest route taken by salesperson visiting various cities during 1 2 hour. Even your optimization techniques are applicable in the case of you might be doing your online shopping, and there also optimization techniques are used to in order to assign the delivery boys, or you might be using Swiggy. These are the new application areas which has emerged as a part of your application of engine optimization. Okay, so the next is optimum production planning, controlling and scheduling. Next, analysis of statistical data, building empirical model from experimental results to obtain the most accurate representation of your physical phenomenon. So you might be doing your BTech project, or some summer internship at certain industry, or inside the college, or inside the laboratory. So whenever you are doing certain experiment, then in that case also you wish to obtain certain best result, or it is the desired result. So we conduct certain experiments, trial and error. Then we what we do, we tabulate, and we use different techniques to in order to find the optimum value of under the given circumstances. Similarly, next maybe this may be also be used in chemical processing equipment, optimum design of chemical processing equipment and plants. Next is a design of optimum pipeline network for process industries. Then we have selection of the site for an industry. Okay, so there may be a number of variables on which the site of an industry may be decided. Then we have planning of maintenance and replacement of equipment in order to reduce operating cost. Then we have inventory control. So likewise, there are numerous application areas of engineering optimization. These are few more: allocation of resources or service among several activities in order to maximize the benefit. So this you may see this kind of arrangement is being done by Swiggy or Zomato. They are also allocating resources, or they are assigning delivery boys based on in order to maximize their profit. Okay, then we have controlling the waiting time and idle time, and the queuing in production time line to reduce the cost. Okay, so waiting time or idling time is also reduced using your optimization techniques. Then we have planning the best strategies to obtain maximum profit in the presence of a competitor. Okay, so planning means there are two competitors like Zomato and Swiggy. Okay, so there is also competition between the two competitors, that who can provide the services at the least cost, and they are also able to maximize their profit. So this kind of things or planning are done or can be done using your optimization techniques. Then in the last, I have mentioned optimization of control system. So it may also be used in electrical system, in electronics also. It is widely used in order to get the optimum values under the given circumstances of any control system. Okay, so this is in brief, as I told, about the critical portion, which is mentioned as introduction to engine optimization under the module 1. And now I will jump to your module 2, uh, which will talk specifically about your optimization techniques specifically. Okay, so let us come to how an engineering optimization problem looks like. Okay, so in the case of any optimization problem, it has certain variables. So let us take this example, an optimization or mathematical programming problem, which is stated as x equal to there is certain value which is function of x1, x2, xt. We are supposed to minimize the x1 this function fx subjected to certain constraint. Gix is less than equal to 0, LG, LJS is equal to 0. So where I is varying from 0, 1, 2, 3, 4, 5. Sorry, this 0 is uh, typo error. This will be 1, 2, 3, 4. Similarly, in the case of J, 1, 2, 3, 4 up to M, up to P, certain value P. So here, x is n dimensional design vector, and fx is termed as your objective function, and G, I, and Lj are known as your equality and inequality and equality constant. Why G, I, X is called as inequality constant? Because here it is not a certain exact value is not available. There are a number of values which will satisfy the solution, that is Gix is less than equal to 0. But in the case of Ljx, because it is equal to 0, so it may be called as your equality constraint. Okay, so this way uh, uh, this way we this your mathematical problem or your optimization function fx is being minimized, give, subjected to certain constraint. Okay, so here also one thing is also notable here. N, M, P, all are independent variables. They are not, dependent in any sense on each other. Okay, so here M, N, and P, all these three variables are independent variables. Okay, so this kind of problem is called as your constraint problem, because what we are doing, we are maximizing certain function. Sorry, we are minimizing here. The objective function is minimization of fx. So we are minimizing certain objective function fx subjected to certain constraint, that is gix or ljx. Okay, there may be also there may be also a case of unconstrained optimization, where we are minimizing the same function, that is x equal to x1, x2, xn, which minimizes the objective function fx, but there is no constraint. There is no constraint applicable to this objective function. So this kind of problems are called unconstrained optimization. But in real life, normally problems or the techniques which are developed, they are they are based on your constraint optimization techniques. Because in any you know uh, suppose I will take example of your any wire drawing process. So there is some in wire drawing there is uh, a die diameter or a die radius. So it has certain value. It cannot be any arbitrary value. We have to we have to draw the wire through a die opening. Then we will have certain fixed value, or there may be a range of a diameter which is required from a wire drawing or a wire drawing process. So in real life, the problems are normally constraint problem. We have certain constraint, like that the die diameter cannot be more than 2 mm, or the there may be other constraint also that we will take up. during the discussion of uh, your problems in uh, optimization. Okay, so in while discussing about engineering optimization, we will get problems normally like constraint problem. Okay, so all the techniques which are developed under optimization or under OR, all these are mostly constraint optimization techniques. Okay, so this is the case of unconstrained optimization when there is no specific constraint applicable to your objective function. Okay, so then we have next uh, in this module 2, that is the design vector. So in any engineering system or component which is defined by a set of quantities, some of which are viewed as variable during the design process. Okay, so these variables these quantities are usually fixed uh, at the outset, and these are called pre-assigned parameters. So there may be some quantities which are fixed and which are variable. Okay, so the quantities which are fixed, these are called pre-assigned parameters, and the remaining other quantities which are treated as variable in the design process are called as design variable or decision variable. So uh, these are again called as design vector. Okay, because these are the quantities which are going to vary during your uh, optimization process. So I will take one example of your uh, uh, gear pair. It is a matching of two gear pair, which is having number of teeth T1 on gear 1, T2 on gear 2. Uh, Distance between the center distance between the center of these two gears is T. Pressure angle phi, psi, tool profile and material. Okay, so we are having number of variables in this uh, gear meshing or gear pair arrangement. These are T1, that is number of teeth on each gear, T1, T2, and also face width. This face width as B. Okay, so these are the variable face width B, number of teeth on gear gear 1, that is T1, number of teeth on gear 2, that is T2. Distance between these two gear center of these two gears is T, and uh, the pressure angle is psi. Then and we have tooth profile and material. So out of these variables, what we are doing, suppose we have fixed center distance d, pressure angle psi, tooth profile and material of your gear. So suppose we have fixed these while designing the meshing of these two gear pairs, we have fixed in advance, and the remaining values will be your phase this phase width b, uh, number of teeth on gear 1 and number of gears on teeth 2. So these will remain the values which may be chosen as per our your design objective. Okay, so in any production unit, wherever we are producing the gear pairs for such kind of arrangement, what we have done, we have fixed center distance, pressure angle psi, tooth profile we have fixed, and material of gear. These we have fixed, and we have variables which are varying. These are B, T1, T2. Okay, so these may be represented as a design vector. I have wrote as transpose of your matrix this B, T1, T2, T1, T2, because normally we represent the any objective function like this: x equal to x1, x2, xn. So in terms of your optimization, techniques, this for this particular gear arrangement, this function will become x equal to p t1 t2. Okay, so since for the the convenience, I have wrote like this: transpose of p t1 t2. Okay, so here also we have certain possibilities, because this is our design vector, or your what we call it as design vector. Sorry. So this design vector, uh, in this design vector, we have no restriction on the choice of your face width, number of teeth on tooth one and teeth one, and number of teeth on uh, gear 2. Okay, so on gear 1 and gear 2, we do not have any restriction on the choice of your B, T1 and T2. So these any value corresponding to B, T1 and T2. So if any unique value corresponding to B, T1 and T2 will create one set of your possible solution. Like I can say that B equal to 2 centimeter, T1 equal to 10, and T2 equal to 20. So this will create one possible solution corresponding to your given problem. Okay, so similarly, there may be n number of years available. Okay, n number of choices available as a part of solution for this gear pair arrangement. Okay, so here I have wrote it as n dimensional. Suppose there are n pairs of solution available, then it may be there may be n number of design vectors. Okay, so under these n number of design vectors, we may come across certain situation that there may be a possible solution as well as impossible solution. Because suppose I have taken in the first, as for example I have shown for first, suppose b equal to 1 centimeter, t1 equal to 20, and t2 equal to 40. So it is an possible solution. It the face width can be 1 centimeter. The number of teeth, since it is whole number, it can be 20. Also, number of teeth on gear 2, that is 40. It is also a whole number. It is also possible. Okay, so this particular kind of design vector may be termed as your possible solution. Okay, so while there is also one possible combination, one set, here the value is p equal to 1 centimeter, t1 equal to minus 40, and t2 equal to 40.5. So for clarity, I have taken also one impossible solution example. Here we can see the set, this design set, under this design set, b equal to 1 centimeter. It is possible. uh, T1 equal to minus 40. So we can easily understand that the number of teeth on any gear profile cannot be negative. Okay, it is very clear. As a mathematics, we can have positive or negative number both, but in real life, the number of teeth cannot be negative or zero. It cannot be zero. Okay, so here what is the this because of this negative value of number of teeth on gear T1, it is making this profile as this design vector as impossible solution. Similarly, you can also see here The number of teeth on gear 2, that is T2, it is written as 40.2, sorry, 40.5. So again, we can see that this T2 also cannot be a fractional value because it is number of teeth. Okay, so number of teeth cannot be a fractional value. Therefore, it is also making this solution, this set of solution, to be a impossible solution. So here, this way, we can understand that in any optimization techniques, the problem seems like this: x1 equal to, there may be certain variables x1, x2, xn up to xn, and there are certain constraint uh, constraint. So these constraint may be equality constraint or inequality constraint. It's like in the case of this gear profile, the what may be the value for what may be the constraint applicable to this process. B, this the constraint may be B is always greater than 0. B, this phase width should not be 0. So any value which is greater than 0 will be a constraint in the case of your this teeth meshing. Okay. Similarly, this uh, about T1. So about T1. So T1 also, in the case of, there may be certain desired number of T's. We may say that at least there should be 10 number of T's or 20 number of T's. We may put optimum value depending upon the diameter of your gear arrangement. Okay, so we may give certain values that number of teeth should be minimum. It should be 20, but it should not be more than 100, because 100 is also a possible solution. But cutting 100 teeth will require a lot of time, and it it suppose it may be up to 200 also. But in that case, what is going to happen? The production time for that particular gear will also increase. So we may give certain restriction that the constraint which we may give, that the value of number of teeth on here T1 may vary from say 10 to 30. Okay. Similarly, because your second gear, that is T2, it is having larger diameter. So we may give constraint, we may assign constraint that number of teeth on this particular gear, that is gear 2, it may be between 20, say 20 to 60. Okay, so these kind of constraint we have to apply, and also we have to, we suppose we are giving conditions like this, that the number of teeth is less than 60. So then we have to also give certain condition that there is a minimum value, obviously, which may also be equal to 0. That number of teeth cannot be less than 0. Okay, so that in that way, whenever we are preparing the set of design vectors or the possible solution, we will omit the we will omit the impossible solution. Okay, so one more things that is that could have been missed, that the number of keys cannot be a fractional part. It is always a full number, that is okay. So it cannot be a fraction part, part like point 0.1, point 0.5, point 0.7. Okay, it is always in the in 1, 2, 3, 4, something like this. Okay, so all these kind of constraint and are applied in your real engineering problem. Okay, so I took very small example. We will discuss about you know about the design part and how these techniques are applied in the next lecture. We will discuss. Okay, so here we can see that normally all the engineering problems are your constraint problem. They are having certain constraint. Nothing, uh, they cannot be optimized under the condition of unconstrained optimization. Okay, so in all your optimization techniques, we will study these constraint type optimization problem, and also one property that which I already told during your introduction part, that suppose we have studies and a minimization problem, that is we know certain techniques which is developed for as a part of your minimization of certain objective function, and we have a problem where we want to maximize certain objective or certain value. So what we have to do, we will simply multiply it by minus 1, and we will conduct the minimization function on that particular available function. Okay, new function. Okay, so that way we can use the minimization techniques for maximization also, as well as maximization techniques into minimization problems also. So this way we will proceed ahead, and for today, we will stop here, and we'll continue to the design constraint on discussion on design constraint in the next lecture. If there are any query, I would like to handle. Uh, Students, if you are having any query, you can ask. Till that, I can download the attendance. Any query? Okay. So those who are having query, they may ask. Otherwise, you may leave. It will be great. This course is going to be very interesting for all of you. You may apply this course in all, whenever you are going in any industry or organization. These techniques will be useful for all of you. So I would like to interact during the lecture also. If you want to, if you have any doubt, you may stop me even during the lecture. Yes, Khushbu, I cannot hear you well. Hello? Okay, okay. So just, yes. So you're, okay. So here you can see, you take it as your x-axis and it is your y-axis. Okay. So we have a certain function fx which we have drawn like this. Okay. So just a minute. Okay. So here first let us take example of your multiplication kind of thing. Suppose we are multiplying function fx by certain constant. Okay, so what will happen? The all the points on this function will be multiplied by certain value, and this curve will shift to a new curve. Okay, this is your cfx. I think you are able to see this my mouse movement. Okay, so here we can see the optimum value was at this point. This curve is not shifting towards left or right of your this x star value. You can see here. If we are multiplying each point on this function by certain constant value, this curve will not shift on either left side or right side to this x star value. So we can say the value is not going to change. Optimum value is not going to change even if the objective function is multiplied or divided by certain positive constant. Okay, so why this is positive constant? It is written if we multiply or divide by negative constant, then this will become your another type of problem. This may become your if it is a minimization case, then it may become by a maximization case. Is that clear? ठीक है. So similar is the case of addition or subtraction. We are adding certain positive value on fx in this curve. Okay, so what will happen? This curve will move upward slowly, but the all points will remain in the same curve. Okay, so same also this positive value, this optimum value will not change. Okay, so any other question? Okay, I will expect that you all remain interactive during the class of this optimization techniques, because it is entirely different than the course which I have taught earlier, that is metal forming process. Okay, there you could cope up the things by using your slide, but here without discussion you may not be able to understand the concept which is needed during the lecture. Okay, so for today I will stop here, and we will meet for the next class, and we will continue the discussion on design constraint in the next class. Okay, so thank you all. We can stop.